Now test for 3 points to be collinear. The necessary and sufficient condition for 3 points with position vectors A, B, C, vector A, vector B, vector C, to be collinear is that there exist scalars x, y, z, not all zeros, such that x times A vector plus y times B vector plus z times C vector is equal to 0 vector, where x plus y plus z is equal to 0. To explain this, if A with position vector A, B with position vector B, and C with position vector C are collinear, then AB and AC are also collinear vectors. That is, OB minus OA is equal to lambda times OC minus OA, which gives OB plus lambda minus 1 times OA plus minus lambda times OC is equal to 0, or lambda minus 1 times A vector plus B vector plus minus lambda times C vector is equal to 0, where x plus y plus z, x being lambda minus 1, y being 1, z being minus lambda, becomes x plus y plus z becomes 0. Hence the result. Conversely, if xa plus yb plus zc is equal to 0, where x plus y plus z is equal to 0, we have z is equal to minus times x plus y. Substituting for z in the given relation, we get xa plus yb minus x plus y times c vector is equal to 0, giving thereby c is equal to x times a plus y times b upon x plus y, which shows c, whose position vector is c, divides the join of a and b in the ratio y is to x. Or in other words, a, b, c are collinear. Note that A, capital A is represented by vector A. Similarly, B is represented by vector B and C is represented by vector C. The dot product. Scalar or dot product of two vectors. Definition. Scalar or dot product of two vectors, vector A and vector B, is the real number modulus of A into modulus of B into cos theta, where theta is the angle between the vectors A and B, and theta lies between 0 and pi. It is denoted by A dot B or A comma B within brackets. Now, geometrical interpretation of dot product is as follows. The scalar product of two vectors is the product of modulus of one and the length of projection of the other in this direction. If A is equal to OA vector, B is equal to OB vector, and angle AOB is equal to theta, then A dot B is equal to modulus of A into modulus of B cos theta, which can be written as OA length OA into length OB, and cos theta becomes OL upon OB, where BL is perpendicular from B on the direction of OA. Therefore, it is equal to OA into OL, which is equal to OA multiplied by the projection of B on A. Alternatively, that will be equal to OB into OM, which is equal to modulus of B into projection of A on B. An important corollary follows. Projection of B on A becomes A dot B divided by modulus of A, which can be written as A cap dot B, Corollary 2. Projection of A on B can similarly be written as A dot B divided by modulus of B, which can be written as vector A dot B cap.